Welcome to the 12th lecture. So, we have been discussing about the rotational kinematics. So, let us continue with that. So, if you remember that in the last lecture we proved using the vector method that C dot B slash A equal to minus omega cross B slash A times C B slash A. So, this is the transformation matrix from A frame to B frame. Similarly, this is the angular velocity of the B frame with respect to the A frame, and this is the rate of change of the matrix C. Now, the same thing can be proved also using the vectrix method, and this I am doing because the vector method we assume that the vector to be fixed and it may create confusion. So, it is better to look from the vectrix method. So, we have in the vectrix method this is your frame A, and frame B is oriented with respect to this. Somewhere this is your frame B, okay, this is frame A. So, if B where f A, if you remember that f A we have written as, let us say A 1 cap, A 2 cap, A 3 cap, or either we can also write in terms of f A tilde equal to E 1 cap, E 2 cap, E 3 cap. So, these are the unit vectors along the direction 1, direction 2 and direction 3. Similarly, in the B frame you will have f B tilde, this will be writing as B 1 cap, B 2 cap and B 3 cap, where B 1, B 2, B 3 these are the unit vectors, they are all unit vectors, and this is called the vectrix as earlier we have denoted it. So, this is the first direction of this is the second direction, and this is the third direction of this of the B frame. So, using this relationship, this is transformation of this triad f A to triad B, okay, where the triad B is rotating with respect to triad A. If we take the transpose of this, so we get f B transpose here, and f A transpose comes here, C B A transpose goes on this side. Now, this can be rewritten, what we can do that we multiply on both sides by C B slash A. Okay. So, if we multiply, so that this quantity is nothing, this is the rotation matrix. So, its a determinant if its a product will be I, the identity matrix, and therefore, we have written here as f A this is f A transpose. So, this is f A transpose here. So, f A transpose this becomes equal to f B tilde transpose times C B A. So, this is written here in this place. Now, as we know that this frame is fixed and frame B is rotating. So, if we differentiate this, so this becomes f A tilde dot, this will be equal to 0. In the earlier case we have taken as the vector. So, it may that might have created some confusion that if that vector is rotating, then what will happen. So, for removing that confusion, we are just dealing with the vectrix. So, both the methods you just compare and have a deep insight how the things are working. So, f dot A transpose this equal to 0 on the left hand side, and the right hand side we will have f B tilde dot transpose times C B slash A times f B tilde transpose times C B slash A dot. Okay. So, what we get from this place that f tilde B transpose C B slash A equal to C B slash A, and here f tilde B transpose this equal to minus with minus sign, and this is the quantity we are looking for. So, if we remove this quantity, so our job will be done. So, now we have f transpose C B slash A plus f tilde transpose B times C dot B slash A, this equal to 0. Okay. So, now we simplify it, okay, because frame A is not rotating. this quantity, this is the rate of change of a vector. Okay. So, this is the rate of change of vector b, or here in this case this is the vectrix. So, this we can write as omega tilde b slash a cross f tilde f tilde this is the vector f transpose. So, here it will come as f transpose, okay, f transpose b, and then this is being operated by C b slash a plus f b tilde transpose. Little bit changes it is required here and our job will be done. So, this omega tilde, instead of writing omega tilde, let us write this as omega here. So, this omega, as you know, this will be omega 1 times this is the rotation rate of vector omega, sorry, this is the rotation rate of the frame B with respect to frame A. So, this we can describe in terms of the vector B itself. Okay. So, the components of vector B omega 2 B 2 cap plus omega 3 B 3 cap, we can write it like this, and this can be written as omega 1 omega 2 omega 3 in the form of vectrix V 1 cap V 2 cap B 3 cap. Okay. So, this gets reduced to, we write it like this, omega tilde transpose. So, here we make the difference, like this is the matrix notation and this is just the vector notation we are using, and here we have the vectrix. So, this is f tilde b. Okay. So, this is vectrix b. So, now, if we insert this here in this place, so what we get, the omega tilde transpose f tilde b cross f tilde transpose b C b slash a plus f tilde transpose b times C dot b slash a, this equal to 0. And from here obviously, we need to reduce it little bit, and this quantity we can separate out and write C dot b a. So, what now we have to use here, that we use this result f tilde b omega tilde transpose times f tilde b cross f tilde transpose b. This quantity we can rewrite this as f transpose omega b slash a cross, and this we can show. Let us do this on the next page, maybe that will be appropriate, or either okay, we will go to the next page. So, we have to get this quantity b slash a transpose f b cross f transpose b. Okay. So, if you write this quantity already we have written omega 1, omega 2, omega 3, and this is f b cross. So, this quantity together if you multiply, this will get reduced to the format, say the here f b is your f b tilde, just put it here in this place, f b tilde is a vector. So, this is b 1 cap, b 2 cap, b 3 cap, and this transpose b 1 cap, b 2 cap, b 3 cap, and there is a cross sign also. So, now if we take this cross product, so b 1 times b 1, that will be 0, b 1 times b 2 is b 3 cap, b 1 times b 3 is b 1 times b 3, this is minus b 2 cap. Okay. So, if you keep multiplying, so this is what you are going to get, this is skew symmetric matrix, and so the third term, second row third term, this is b 2 times b 3 equal to b 1 cap. Okay. So, here this will be minus b 1 cap, and in this place b 2 cap. So, remember in the skew symmetric matrix, in any column or any row only one minus sign will be there, and the other will be plus 1, and obviously there is 1 0 all the way if you look. So, we can just insert here in this place 0 B 3 cap minus B 2 cap minus B 3 cap 0 B 2 cap 0, and then multiply it and solve it. So, after solving you get it in this format. So, omega 1 after we multiply it. So, minus omega 2 times B 3 cap, this is the term getting multiplied with this, we are multiplying this, plus omega 3 times B 2 cap, this is the first term. Okay. So, this will be a single row and there will be 3 columns in this, the other will be from here to here if we look into this. So, omega 1 B 3 cap, then omega 2 this is 0, omega 3 minus omega 3 B 1 cap, and the third one will be omega 1 B 2 cap with minus sign, and this one omega 2 times B 1 cap, and this the last one will be 0. So, you get the these 3 terms. Now, these 3 terms if you rewrite it in terms of, if you change the order, okay, if you write it like this, okay, on this side, then you will have here 0 omega 3 minus omega 2 0 0, and here omega 1 minus omega 1 omega 2 and minus omega 3. So, thus the things have got reversed. So, what this quantity is? This quantity is nothing but B this is we have written as F B, either in the form of tilde or transpose, whatever you write. Okay. So, F B tilde transpose, this is the quantity, and this quantity is nothing but minus this quantity is minus omega tilde cross, okay, because in the omega tilde cross minus sign comes here, here this minus sign. So, the things have got reverted. If you put take out the minus sign, you will see that here it will be minus plus, and similarly the other places. So, this is the quantity that we are getting. So, this can be reduced to this format. So, what we are getting omega tilde transpose B slash A F B tilde cross F tilde transpose B, this equal to minus F tilde transpose B times omega tilde cross, and this can be utilized in the expression that we have got. So, inserting this in the equation that we have written. So, our equation was F tilde B transpose times C dot B slash A plus omega tilde transpose B slash A F B cross F B transpose, either you can write both way in terms of tilde also, it does not matter here, and the quantity from here to here right now we have derived this, and this we have written as let us check the sign here, perhaps sign reversal has taken place. So, this part is okay, and if we multiply this comes here, we will check the sign here whether the things we have done correctly or not. So, B 1 cap, this is 0, B 2 times minus omega 3, here it comes as B 2 comes with plus sign. So, here we will have plus, here minus, plus, here the sign got reversed, this is minus and here minus. So, this is okay, this is plus. So, what we get here, this quantity should be plus, not minus. So, we have done this correction. Now, using this we can replace this whole part. So, we pick up this particular part f tilde transpose b times omega cross, okay. F tilde transpose, this is f tilde transpose b times omega b slash a tilde cross, okay. And then this is c b slash a, right hand side this is 0 and this is f b tilde transpose c dot b slash a. Now, what we see that this quantity is common to both these terms. So, we can take it outside and write inside c dot b slash a plus omega tilde cross c b slash a, this equal to 0. So, if you look here in this quantity, the right hand side this is 0 and this is non-zero quantity, because this is the basis vector. This consists of basis vectors, that is this is a vectrix. So, this is non-zero quantity and therefore, this quantity must be 0, c b slash a omega tilde cross c b slash a, this equal to 0, and this is what we proved using the vector method. So, either using this method or that method, there we assume that in the frame A there is a vector which is fixed and then the frame B which is oriented with respect to this frame, okay. This is frame B and this is frame A. So, B is rotating with respect to this and the vector was fixed. However, here removing this vector we have just assumed the frame and then derive the whole thing. Equally, in the case of the, in this case we could have assumed that this the frame A, this vector A is there, say. So, this vector A will have certain components along the 3 directions, is not it, and if the frame B is rotating with respect to frame A, okay. So, obviously, if we have already fixed the components here along this direction, so in this frame these components are not going to change. So, this method and the vector method, they do not differ, they are exactly the same, only thing it is a matter of representation how we are going to work out. One may be convenient for some people, another may be convenient for some people. So, this vectrix notation you have to get acquainted with, then only it will look convenient, otherwise for many people this appears to be little complicated. So, if you are not comfortable with this, you can just follow the vector method that we have discussed in the lecture 11th. Okay. So, once we have done this, so the next step will be to okay, our next step will be to get the C matrix in terms of already we have the C matrix. So, what we require, that we need interconversion. Say we have the, now we are dealing with the kinematics of rotation. So, we will be dealing with phi dot, a tilde dot, c tilde c dot, these are the things we will be handling here. Okay. And quite often it may be required that we convert, we go from one notation to another notation, that is sometimes we may be dealing with C and from this C we need to go to the a tilde dot and the phi dot and vice versa. Sometimes it may be that we are dealing with a dot phi dot and from there we need to go to the C dot. And as you will see, what we are doing, it is not just without purpose. We are going to, we have already discussed about the Euler's parameter. So, Euler's parameter of epsilon tilde we have written as a tilde sin phi by 2 and eta tilde equal to cos phi by 2. So, our objective ultimately is to get these quantities. Okay. So, once we differentiate these quantities, you can see that a dot will come and phi dot will come. Okay. And a dot, now it is described in terms of the c dot if you have the C dot and the vice versa, whatever we want to do. So, the thing is that we need to go from this place to this place, or either this place to or from this place to this place. Okay. And the same thing can also be done in terms of the quaternions. So, let us proceed further. So, if you remember that using this C equal to cos phi I plus 1 minus cos phi times A tilde A tilde times A tilde transpose minus sin phi times A tilde cross. This is the C matrix, and this we have also converted into the in terms of the Euler parameters. Okay. So, still what we do here, that we have from the previous slide, from here what we get, something is missing out. Okay, we carry it to the next phase, omega tilde cross, this quantity is omega tilde cross times C b slash a, this will be equal to minus C dot b slash a, and multiplying on both sides by C b a transpose. So, this will get reduced to identity matrix on the left hand side, and this will be C b slash a times C b slash a transpose. And if we drop this notation, so simply we can write this as C dot times C transpose. So, omega tilde cross this gets reduced to minus C dot times C dot transpose, and this is one important conclusion which will be frequently used. Okay. So, using this particular expression, omega tilde cross this equal to minus C dot times C transpose. So, if we insert this, okay, this C needs to be inserted here, and derivative of C, after taking derivative of this C, this needs to be inserted here, which will do as a part of the tutorial. So, it can be reduced to the format omega tilde cross, already last time perhaps we have written it, A tilde cross minus 1 minus cos phi and if the cross notation is taken off from both sides, then this gets reduced to phi dot A tilde minus 1 minus cos phi A tilde cross times A tilde dot plus sin phi times A tilde dot. Okay. So, if you know A dot, okay, obviously you are rotating about the A vector. So, this needs to be available, this should be available. So, A tilde dot phi dot, these are the two things which are main. So, if these two things are available and by how much angle you are going to rotate, so this will give you the omega, and vice versa, if the omega is available. So, also we can go and find out A tilde dot and the phi dot. Now, if we are looking for rotation about, this is say as we have shown last time, that if this is my frame and here this is your omega vector and this is A vector. Okay. So, component here in this direction, this will give you the phi dot, the component of omega along the A vector, this is nothing but our phi dot. So, if we take the component of omega along this direction from this place, so this must result. And therefore, if we take the omega tilde, this is available to us, and we take the component of this along the A directions, means A tilde transpose. We have to write like this. Okay. So, this matrix, then we have to multiply it by A tilde transpose, and if we do this, okay, so we get on the left hand side this is the phi dot. This is obviously a scalar quantity, okay, because this is the inner product. So, here we will have A tilde transpose times phi dot A tilde is 1 minus cos phi okay. So, if we take it inside the bracket, so phi tilde dot this quantity becomes 1 because A tilde is of unity magnitude, then 1 minus cos phi, and this gets here we have to write it like this, and plus sin phi times A tilde transpose times A tilde dot. Now, A tilde times A tilde transpose times A tilde, this quantity is I, this quantity is 1. Okay. This is a scalar inner product. So, the right hand side, this is a constant. Okay. If we differentiate this, this will be 0, and this is the inner product. So, what it implies, this can be written as, if it had it been the outer product, say this quantity, if we write it like this. So, this is not equal to A tilde dot A tilde times this quantity is not equal to this quantity. See the difference. This is the outer product. Okay. A tilde dot is coming here in front, here it is a coming at the end. But here in this case, because it is an inner product, if this will basically give you the term like A1, A2, A3, and here you have A1 dot, A2 dot, A3 dot. So, if you take this A2 dot plus A3 times A3 dot, and you know that I can put it in the front. So, because it is a scalar quantity, so it does not matter, okay, and this can be written as A1 dot, A2 dot, A3 dot times A1, A2, A3. Okay. So, these two quantities are equal, and therefore, we can write like this, and therefore, this implies here A tilde dot times A tilde, this equal to 0, or equally we can say this equal to A tilde transpose times A tilde dot. Okay. So, this simple conclusion it can be used here. So, this quantity gets reduced to 0. Here we have the dot. So, this quantity gets reduced to 0, and we just have to look into this quantity, which is phi dot minus 1 minus cos phi, and this quantity again we have to resolve it. So, phi dot 1 minus cos phi phi dot equal to here ultimately what should happen, that this quantity should go to 0, because here only then what we get here phi dot equal to phi dot. Okay. This phi dot, obviously on the right hand side we are getting here phi dot because of this. Okay. Now, here if we prove this, that this quantity is 0, this part, okay, then only our job will be done and the left hand side will be equal to the right hand side. Otherwise, this will be extra term and then things will be in error. So, what it says that the component of omega as we have discussed earlier in the direction of A tilde is nothing but this phi dot. Okay. And this if you can prove, okay, your job is done. So, what it needs to be proved that A tilde transpose A tilde cross times A tilde dot, this quantity is 0. Okay. So, we go to the next phase now. So, we need to prove that A tilde transpose A tilde cross times A tilde dot. A tilde transpose times A tilde cross times A tilde dot, this equal to 0, this we need to prove. Okay, so, we will continue in the next lecture. Thank you.